Okay, so we've been just looking at limits and looking at them graphically and what that meant. And so now we're going to jump
Oh
in
yeah,
and
so
look
for
at,
like this question that we just did, like not too long
yeah.
ago, did we just
Mhm.
skip part four? Oh wait, no, part three? No, part four. I don't remember. It was one of those.
So we actually did all three parts. We looked at the first part, which is the limit as x is
Hmm.
approaching -1 on the left. We did right here as it is approaching on the right.
Okay.
For part 3, we did it in order for the limit to exist. We have to show the left and the right are the same. And then
Okay.
part 4 is plugging in the value here. So this would have been part 4. So we did get
Oh,
to all of them.
okay. And then what's the
Did
difference
you have
between
any
a open
questions?
circle and a closed circle?
So an open circle means that you're getting really, really close to that point, but it's actually doesn't exist at that point.
Okay, and then the
And
closed circle
so
means
like
it
for
does
x
exist.
equals -2. Exactly, exactly.
Okay. Okay.
Any other questions on those? Good questions. Okay, so let me jump down. I kind of copied and pasted in. Actually, maybe before we jump into, again, algebraic, we can also look at limits as they go to positive infinity or negative infinity. So basically, we're not looking at one particular x value that the graph is going towards, but we're looking at the end behaviors of the graph. So as we're looking at the graph here, so this is asking, look at this graph. And when you're going to positive infinity, what value is your y value going to? And so notice this dotted line, this horizontal line, excuse me, at x equals or y equals 3. That's a horizontal asymptote. And so what that means is when my graph in this case is going to positive infinity, this graph is going to be hugging this line. It might cross it, but it's still always going to be hugging that line. And so the limit as x approaches or goes to positive infinity, this y value is getting closer and closer to or equaling 3. So that limit is equal to 3. Let's look at the limit as x approaches negative infinity for that graph. So we're looking at the left-hand side, the end behavior of that graph. So in this case, notice that this graph shoots downwards. This arrow is telling me that this is going to go in this direction forever. And so if I'm shooting downwards like this forever, I'm not getting to one particular or getting closer to one particular y value. This is going to go to negative infinity. And so we would say that this is equal to negative infinity. When a graph doesn't go to one particular value, it actually doesn't exist. We like, though, to say where it's going, if it's going to negative infinity or infinity, because it just kind of tells us more about the graph. So as your x values go to negative infinity, the y values on the graph go to negative infinity.
So on the test, are we gonna have to like put an explanation with our answers?
No, for in this case, you could be fine with just saying negative infinity. I know what you're talking about, and
Okay.
that you really don't have to show. Just for explanation for the class, seeing it the first time. That's the only reason I'm writing it in.
Okay. So for like the second one, would it be the same thing? Like it just no.
So like right here,
Mm-hmm.
this too, we could tell without showing any work
Mm-hmm.
that this is going to 3. So you're fine with not showing work. For homework, you guys are supposed to be showing work while you're doing homework. Well, stuff like this, there's nothing really to show. So if you want, like if that was like from problem 1 through 10, they were graphed like this and you really didn't need to show work, you're welcome to just say, you know, problems 1 through 10, no work needed on 3.1. And then jump to the problems where you have to actually show work to get the answers. Okay, so let's look at that second graph of g of x. So this one's saying, look at the limit as x approaches negative infinity of g of x. So we're looking at the graph. And as x is going to negative infinity, we want to see what is your y value going to? Is it going to any particular value or not? Well, notice this graph, it has an arrow. Again, that's meaning that that's the direction that it's going to head forever.
Yeah.
And so what y value is that going towards? Is it going it towards any y value? This is going this way forever. So it's not particular, getting closer and closer to a y value. It's going to positive infinity, right? And so technically we would say it doesn't exist, but again, a lot of times we want to know a little bit more about the graph, and saying it's equal to positive infinity tells me what's going on my end behaviors at the left-hand side of the graph. So let's just extend this and say, let's look at the limit as x approaches positive infinity of g of x. So in this case, as we're going, x is going to positive infinity, follow the graph, see if it's going towards any y value, and it's not. It's also shooting upwards. Your y values are getting larger and larger, and so this is also going to positive infinity. And we would say this doesn't exist. So again, we can look at the limit as x approaches some single value, or we can look at the limit as x goes to infinity or negative infinity. Okay. See if I can find it. Okay, so we've already kind of talked about this. So this is a limit of f as x approaches a may not exist. So let's just read through it real quick. So it says that the limit of f of x becomes infinitely large in magnitude, positive or negative, as x approaches the number a from either side. We will say that the limit as x approaches f of x equals infinity, or we will say that the limit as x approaches a of f of x equals negative infinity. But in either of these cases, the limit doesn't exist. So positive limits don't exist. We actually didn't look at a case like this. Let's look at what this is saying. So this is actually saying x is approaching a single value of a. So let me look at graphically. So let's say that this is x equals a. So technically on the graph here, there's going to be a vertical asymptote. Usually graphically, you will denote that with a dotted line, but you don't see it on the graph technically. And so let's say you had some graph that looked like this, where it's coming up here and then shooting upwards. And maybe over here on this graph, looks like this. And let's say that this is f of x. So notice if I look at the limit of this graph as x approaches a on the left-hand side. So locate x equals a on the graph. Left-hand side, go to the piece on the left of a, which is this. And notice that that's shooting upwards. It's not going to one particular y value. And so since it's not going to one particular y value, then this is equal to, and it's shooting upwards, it's going to positive infinity. If I look though at the limit as x approaches a on the right-hand side, notice that piece of the graph is shooting downwards. It's not going to any particular y value. On the left hand, follow the graph, and it's shooting downwards. And so this piece is going to negative infinity. They both don't exist because that's not going to one particular y value. Okay, so that's one case. If f of x becomes infinitely large in magnitude, positive as x approaches a from one side, and infinitely large in magnitude negative as x approaches a from the other side, then the limit f of x approaches a does not exist. This is an actually example that we just did. And then last thing. If the limit as x approaches a of f of x equals L, and the limit as x approaches a from the right is equal to m, and those numbers aren't the same, and that's what we were looking at, limits of the left and the right not giving us the same value, then we said that that limit also didn't exist. Okay, so these limit rules are going to be helpful for us, and I should pause this for a little bit so that you guys can get these down. And let's just kind of maybe go through step by step, and I can explain a little bit of it. So let's just look at this. So rules for limit. So this is going to give us rules so that we can look at an equation and figure out, without graphing it, what is our y value going to be as x approaches some number. So rules for limit says let little a, capital A, and capital B be real numbers, and let f and g be functions such that if we looked at the limit as x approaches little a of f of x, and you got capital A, and you looked at the limit as x approaches a of little g of x, this is equal to capital B. So all that's just saying is that the limit exists. As I come in on the left and come in on the right as x equals a, that is going to give me the value of a. This right here is saying if I'm looking at the limit as x is approaching a on g of x, so equation of g of x, so our g of x might look like this, and that value is b. That's all that this introduction is saying. It's saying real numbers, so we're not dealing with imaginary numbers. Okay, so if k is a constant, then the limit as x approaches k is always going to equal k. So recall, if you guys had a graph of f of x equal a constant, or y equals a constant, these are writing it differently but meaning the same thing. The graph of that is just a horizontal line through k. So y equals k or f of x equals k, the graph is a horizontal line through y equals k. So maybe this is k here, and our graph is just a horizontal line through k. So if you chose some value of a here, right, it wouldn't actually even matter where you were on this graph. But if you chose some x value of a, what is the y value you're going to get as you're approaching x equals a on the left and x equals a on the right? That y value is k. So that's what this piece is saying. Okay, so the second piece of part A is saying the following. So if you have the limit as x is approaching a, and you have some constant k times a function f of x, then basically we can pull this constant outside of the limit and just look at the limit of x approaches a of f of x. Once you found out what that value was, you just multiply it by the constant in front. So let's maybe look at the following. If I was looking at f of x equals 2 times x. Okay, so if I graph this, this is a linear line. It's in the form of y equals mx plus b. You can plot points also if you need to. My y-intercept is where x is 0. Y is also 0. If I plug in 1, right, I get 2. If I plug in 3, I get 6. So pretend that's straight. So if I wanted to look at the limit of this, let's just look at it first graphically. As x approach, let's just think of one number. How about 1? Of this f of x, which I could say is the same thing as a limit as x approaches 1. Let's just put in the equation of what f of x is in this case. F of x in this case is equal to 2x. Graphically, as we're getting closer to 1 on the left, I'm equaling 2. As I'm getting closer and closer to x equals 1 on the right-hand side, I'm also getting a y value of 2. And so I noticed by graphically the limit as x approaches 1, because the left and the right are the same, this is equal to 2. What this rule over here was saying is, okay, we can just take this limit here. 2 is a constant. We can take this 2 outside and put it in front. So this is 2 times the limit as x approaches 1 of x. Okay, I might have to go to the next rule so that we know what that is. Sorry. Basically, you just plug in that value of x that you're approaching anywhere you see an x in your function. But let me see, make sure that that wasn't one of the rules. Oops. If you have a summation of 2 functions, actually, so basically this rule that I'm using for this next one is number 5. So it's saying if you have a polynomial p of x and you're looking at the limit as x approaches a of p of x, all you have to do is plug in, this will give you the same value of plugging in a wherever you see an x in the function p of x. So using that rule 5 over here, well, x is a polynomial, and I could have even used it here, 2 times x is a polynomial. And so this would be equal to 2 times plugging in 1 here, wherever I saw an x, times 1, which is also equal to 2. Really helpful if you're given a function. This case is pretty easy. So instead of having to go through and graphing the whole thing, and then looking at what side, as we're pushing that x value from the left and the right, are we getting the same thing? Where we could just go in, if we wanted the limit of this, as x is approaching 1 of 2x, we can just go in, because of this rule, and plug in that value of x wherever you see an x in the function and simplify. Basically, this is saying we can think of these as terms. So if you have a polynomial, you have more than one term, and so you're adding or subtracting multiple terms. Basically, you can break this down as the limit of x approaches a of one term plus or minus, depending what it is, x approaches a of the other term, and continue to go on. these are rules. Usually we won't go through and break it down doing these steps. We'll just go in and we'll go in and plug in that value as x is approaching a into our function. So this is basically the next piece saying if you have multiplication. So maybe I have x times x squared. If I wanted to, without simplifying first, I could break it up as a limit as x is approaching a of x times the limit as x is approaching a of g of x. So we can break it down as multiplication. Same thing with division. If you have a quotient, you could look at the limit of the numerator over the limit of the denominator. This is very important that b, what you have in the denominator, can't equal 0. And then let's put a star by this one too. So some of the times when we are doing these limits and we go in and we plug in a number for x and we simplify it, you might get a particular form that doesn't tell us anything. So for instance, if you got something where you got 0 divided by 0, this is an indeterminate form. It doesn't tell us anything about the limit. Oops. Oops, that's anything about the limit. Okay, if you get that form, basically you're gonna have to use some of algebra, and we'll go through different cases that you'll see, but we're gonna have to use some algebra to kind of manipulate and get it in a form where we don't get 0 over 0. Let's just kind of quickly go through these. So limit for any value number k, limit as x approaches a of f of x raised to the k power. This is equal to, instead, we could take this exponent and we could look at the limit and then raise whatever that limit was to that exponent. Sorry. If you have a limit as x approaches a of f of x equals the same thing as a limit as x approaches a of g of x, and your functions are the same, except for maybe x equals a. We can do the same thing with exponents. This is really more helpful when we get, if you were in the calculus class for STEM majors. You'll see more of the last ones. This class, I don't think we're going to see that much of that. Logarithms, though, are really helpful with simplifying things. And so if you have a limit of a log, basically you could pull the log out and look at the limit of the function of what you were taking of the log. And that would give us the log of whatever that value was. Okay, so pretty much these exercises are using those rules that we just had to simplify. So maybe let's try 22. I just pulled these. Again, I don't have my textbook with me in Colorado, so it's just easier if I have things right in front of me. So we could break this down by our rule that says this is the same thing as a limit as x approaches 4 of g of x times the limit as x approaches 4 of f of x. So these actually gave us the limit as x approaches 4 of f of x. That was 9. And the limit as x approaches 4 of g of x, that was 27. So this is going to equal 27 times 9. Thank you, 243. Maybe let's jump down to 26. So this says, and I'm going to break it down. Remember, radicals could be rewritten as powers, or another way that we could do this is by our rule says we could look at the cubed root of the limit as x approaches 4 of g of x. And so if we look here at the limit as x approaches 4 of g of x, that was what I had in green up here. This was 27. And so we're looking then at the cubed root of 27. So what number can you cube and get back 27? Well, 3 times 3 is 9 times 3 is 27. So cubed root of 27 is 3. Okay, one more. So the limit as x approaches 4 of 5 times g of x plus 2 all over 1 minus 4 of x. Sorry, f of x. Okay. So I'm going to break this down. Remember, if we have a quotient, we could break it down as the limit of the numerator. So we could first break it down as the limit as x approaches 4 of this whole thing, 5 g of x plus 2 all over the limit as x approaches 4 of 1 minus f of x. Well, if I have a sum of terms, I could look at the limit of each term. So I could break that down in the numerator right here as a limit. I am showing these steps step by step, but normally I would not do this. I could simplify and do this without. So limit as x approaches 4 of 5 times g of x plus the limit as x approaches 4 of 2, that's just the numerator, all over the limit as x approaches 4 of 1 minus the limit as x approaches 4 of f of x. Remember, we can pull the constant out front. So here this would equal this 5 times, well, the limit as x approaches 4 of g of x. That was what one? 27. So that would be 5 times 27 plus the limit as x approaches a constant is always just that constant 2. All over limit as x approaches 4 of a constant 1 is just 1, minus the limit as x approaches 4 of f of x. That one was 9. So minus 9. Order of operations. Treat the numerator as a parentheses, treat the denominator as a parentheses. Multiplication comes before addition, so 5 times 27, what is that, 35, 135, plus 2. 1 minus 9 is negative 8. And so I have 135 plus 2 is 137, divided by negative 8, which I don't know if that goes in evenly or not. My guess is it doesn't. Did anyone see an error that I did? $17.125. So let me just kind of check my work real quick. Limit, just like make sure I did even the right problem. X goes to 4, 5 times g of x. So 5 times g of x was 27 plus the 2 out here. 5 times 7 is 35, carrying my 3, that's 135. And 1 minus, so 1 minus f of x, which is 9. Okay, so it looks like I did everything right. So you look at what my math lab wants. This doesn't probably have any, that doesn't have any common factors in the numerator denominator. I know 8 is 2 times 2 times 2. I know 137 is an odd number, so 2 isn't divisible in there. So that's as simplified as possible. It might want it as a mixed number. You could put it as a mixed number or a decimal, but just read the directions on my math lab. It could accept it in all 3 forms. Okay, so we did not complete, and I'm okay with that because you guys are just getting introduced to the concepts of limits and stuff. We didn't complete this section. So we really didn't complete any section this week in homework because of going over the syllabus on the first day. So technically no homework is due on Monday, but part of your homework assignment, I actually want you to get in, make sure you're logged into my math lab. If you have to, do your grace period for 14 days. And I would not wait. I would get in and I would start doing the problems that I could and then stop. So just not do anything. Get in, start on 3.1 for the homework. You won't be able to complete it, and I will up the due date to be the following Monday. Okay. So let me just stop the video, and then if you have any questions, you can ask questions, and if not, I'll let you guys go for the day.